Hey, North, Mr. Hugo here. Now that we've talked about buffers a little bit, now we're going to get into buffer calculations. Don't be intimidated by this stuff. It's actually pretty straightforward. The main formula that we're going to use is called the Henderson-Hasselbalch equation. You've seen this before. I showed it to you already. You can kind of see how this is really just a derivation of the k expression, right? Imagine in your mind a little bit k equals h plus times a minus over HA. Do a little bit of rearranging, and this is actually what you get. Take the log of both sides, and you end up with this. We could also write this with a negative log here, and that would flip the fraction. And so because it's often written with a positive log, that's why the base is on top and the acid is on bottom. So just kind of pay attention to that. It's easy to kind of get them flipped around. When you look at the ratio of acid to base or base to acid over here, they're both in concentration, right? But if we think about the context of this, the buffer is one solution. It's in one container. And so the volumes are going to be the same all the time. And so if you think about the units on this, this would be moles per liter and this would be moles per liter. The liters is actually going to cancel out. So you can do moles and moles. It actually doesn't matter what the volume is. The best buffers have a ratio of the acid to base as close to 1 as possible. That maximizes the buffer capacity. If you think about it from the equilibrium reaction equation, if we have just as much A minus as HA, then we can buffer the solution in either direction equally, right? If you have, let's say you dump a ton of salt into the solution and you have tons of conjugate base, but your acid is actually very dilute, you could handle the addition of tons of H plus because it will keep dissociating to the left. It'll just keep going that way. But if you added a bunch of base, you wouldn't dissociate many more acid molecules because there's not that many in there, right? If we have a very dilute solution of the acid. So the best buffer is one that has large concentrations of the undissociated acid and the conjugate base and equal concentrations. In all the questions that we're going to look at, it's really just different things that you can solve for. So we could solve for the pH, which is really just the same thing as H plus. You just have to take the negative log. Same thing with Ka and pKa, essentially the same thing. And then the base to acid ratio, which could be written as acid to base, depending on how you're looking at it. So let's just go through a few examples. If this is our example, we have, we're trying to find the pH. We have a 0.5 liter solution, and it's formic acid and sodium formate. And then we have a Ka for the formic acid. So obviously it helps to identify what our acid and our base is. Let's start there. So the acid is obviously the formic acid and the base is obviously the sodium formate. It actually doesn't matter what the formula of this is. I like to just kind of think of it in terms of HA and A minus and H plus. Now there's two different ways we could go about this. We could use either of our equations. We have a Ka, which is good for this equation. We don't have to take the negative log of it. But we're going to have to find the pH, which is the negative log of the H plus. So we're going to have to do a log anyways. I'm just going to go ahead and do this H plus formula here. So our H plus is equal to our Ka times the ratio of acid to base. And it's really just so simple as plugging in those numbers. Now technically the formic acid is dissociating a little bit, and so the HA is decreasing, but because our Ka is so small, that's a negligible amount. We don't have to worry about it. When you solve, when you just run the numbers and then turn it into a pH by taking the negative log, you end up with 3.89. Notice that the pH has 2 digits after the decimal. That's correct because there's 2 significant figures total in the problem. Now we could also do it this way, where we take the Henderson-Hasselbalch equation and you just plug everything in. Notice that I flipped the base. I put the base on top and the acid on bottom, and you end up with the same exact answer, even to multiple decimal places. All right, so one more example. If we have an acetic acid and a sodium acetate buffer solution, what ratio do we need if we want the buffer to maintain the pH at 5.0? And then explain how you would make up such a solution. So we have a Ka. The Ka is for the acetic acid. So let's start maybe by figuring out what the H plus concentration is. We have the pH, so it's a pretty easy conversion to go to the H plus concentration from the pH. Our acid is our acetic acid. Our base is our sodium acetate salt solution. And so let's do the conversion from pH to H plus. You can actually do this one in your head. It would be 10 to the negative fifth, 1.0 times 10 to the negative fifth. So that's my H plus concentration. I'm going to set that equal to my Ka, which is already given, times my ratio of HA to A minus. Now we don't know either one of these, right? And so it's kind of like we have two unknowns. But we can simplify this because we can think of it as a ratio. Let's simplify it by just thinking of it as x, as the whole ratio is x. If we solve for x, that's 0.56. Now x is equal to our ratio, right? So how would you make up a solution of this buffer? You would just need to make sure that you have 0.56 moles of the HA for every 1 mole of the A minus. So I kind of wrote it like this. You would mix up 0.56 moles of acetic acid for every mole of sodium acetate that you put in. It doesn't matter what volumes you have. It doesn't even matter what concentrations you have because they're in that ratio. Now obviously the buffer could handle more acid or base. It would have a larger capacity if we kind of pack the solution with lots of ions that can accept the base or the acid. But if you have this ratio of 0.56 to 1, then your acetic acid sodium acetate buffer would hover around a pH of 5. And that's related to the Ka, right? If you have a different acid, then you have a different Ka and you would have a different ratio if you wanted to maintain a pH of 5. So that's pretty much as complex as it gets. I mean, we could throw some stoich in there, we could throw some ice tables in there, I suppose, too, but it can be really straightforward and really simple. If you have any questions, make sure you write those down and bring them up in class. Otherwise, this is Mr. Yergler signing off.